Hello, this video is going to be on the limit comparison test, and this is one of the two comparison tests that you need to know in Calc 2 for determining the divergence or convergence of a series. So in another video I went over the direct comparison test. In this one we're just looking at the limit comparison test. So first of all, what the limit comparison test actually says. So the first thing that you need to do is you need to select a comparison series which we will call B sub n. Now this is exactly the same thing that we did in the direct comparison test. You want to select a series, simple series, usually a geometric or a p-series that you know converges or diverges. So you need to select the comparison series and it needs to be something that you know its convergence. All right, then we are going to take the ratio of A sub n, which is our given series, and B sub n, which is our comparison series. We want to find the limit of that ratio. And so, once you find the limit of the ratio, one of three things is going to happen. Number one, it will actually have a limit, which we will call L. All right? So, if the limit as n approaches infinity of the ratio of A sub n divided by B sub n is equal to some limit L, and that limit cannot be equal to 0, that will be the second case, then either both series converge or both series diverge. And since you already know whether B sub n converges or diverges, you're pretty much done. So if you get a limit of L and you know that your comparison series converges, then the given series converges. If you know that B sub n diverges and you get a limit L, then you know that your given series also diverges. The second case is when the limit as n approaches infinity of the ratio of A sub n divided by B sub n is equal to 0. In this case, if B sub n converges, then A sub n converges. Now, some people will say, well, what happens if my comparison series B sub n diverges? Well, then this doesn't tell us anything. We have to go to another test. Third case, if the limit as n approaches infinity of A sub n divided by B sub n is equal to infinity, and if the comparison series B sub n diverges, then the given series also diverges. Once again, what happens if I get my limit of my ratio is infinity and B sub n is a converging comparison series? Well, again, we don't know anything. This test is inconclusive. It tells us nothing, and we need to go on to a different test. All right, so those are the three scenarios. I'm going to do a couple of examples out of my notes. So the videos are already in my notes, but I'm going to do them on the board and explain a little bit more on that. All right. The best part of these videos is just watching me erase the board, I'm sure. So the first series that we want to do will be, we have the series of 1 over the square root of n plus 1. Now, one of the questions that students always have, rightfully so, is how do I know what to compare it to? And I might do another video on limits at infinity, because that, if understanding from Calc 1 limits at infinity is really necessary to being able to decide what to do here. So I might just do another little video real quick after this one on that. So we have 1 divided by the square root of n plus 1. Well, n is actually raised to the 1/2 power. And so the idea here is that we want to look at the most powerful term. And what I mean by the most powerful term is as n gets larger and larger and larger, as n is getting closer and closer and closer to infinity, it's getting infinitely large, which one of these terms, 1, square root of n, or 1, is having the most effect on the outcome? Well, the constants have no effect. No matter how large you get, no matter how large n becomes, 1 is always 1. 1 is always 1. But this term right here is getting larger and larger and larger and larger. So this term right here is the crucial term. As n approaches infinity, this is the only term that really matters. So because of that, this whole thing, I'm going to compare it to b sub n is 1 over the square root of n. That is going to be my comparison series, right? Everything else is basically not important, especially in the denominator. That 1 is not important. So this then becomes my a sub n, and this is my b sub n. So we now want to take the limit as n approaches infinity of the ratio of a sub n, that's 1 over the square root of n plus 1 divided by 1 over the square root of n, which becomes the limit as n approaches infinity of 1 over the square root of n plus 1 times the square root of n over 1. So all I'm doing is a little basic math. Instead of dividing, I am multiplying by its reciprocal. And then we could change that to the limit as n approaches infinity of the square root of n over the square root of n plus 1. Now what we want to do is we want to multiply by the highest power of n. And the reason that we multiply by the highest power of n is because that's the most powerful term. Well, the only power of n is n to the 1/2. So I'm going to multiply by 1 over the square root of n, 1 over the square root of n. That then gives me n times 1 over the square root of n is 1 in the numerator. Same thing here, we have 1 plus 1 over the square root of n. So what we are looking for now is the limit as n approaches infinity of 1 over 1 plus 1 over the square root of n, which is 1. So the limit of the ratio of a sub n to b sub n is 1, which is my L. What that tells me is that they either both converge or they both diverge. So what is it? Well, b sub n is 1 over the square root of n. That is a diverging p-series. So this is a diverging p-series. And the reason it's diverging is because the power of n is less than 1. And so it's a diverging power series, so a p-series. So therefore, my given series also diverges. And we are done. I'll do one more where we have a slightly different outcome. Again, you get the enjoyment of watching me erase the board. Someday I'll learn how to edit these things. I can just edit that stuff out. For now, just enjoy the back of my head. All right, here's one everybody loves. So we have a series of 2 to the n plus 1 over 3 to the n. All right, which means that my a sub n, the sequence, a sub n, the sequence, is 2 to the n plus 1 over 3 to the n. Question is, what should I select for my b sub n? And so what I do is I say, okay, as n is getting infinitely large, this 1 has no significance. It's always going to be 1. But the 2 to the n is getting infinitely large. The 3 to the n is getting infinitely large. And because they're both raised to the n power, they're both getting infinitely large, kind of together. So what I could do is I could say 2 to the n over 3 to the n. But that's kind of messy. I really don't know what that is. But I can rewrite that as 2/3 to the n. And that basically is a geometric series. If we wanted to, we could write it so it looked exactly like the form of the geometric series that we like, which would be 2/3 times 2/3 to the n minus 1. And that would be what I'd want. But basically what I'm just going to go with is this version right here, 2/3 to the n. All right, that's what I'm going to compare it to. But this is how you could make it look like our a sub 1 times r to the n minus 1. Well, let's just go with 2/3 to the n. So that's going to be my b sub n. So I want to find the limit as n approaches infinity of 2 to the n plus 1 over 3 to the n over 2/3 to the n. Now, again, I'm going to kind of backtrack. I'm going to write 2/3 to the n as 2 to the n over 3 to the n again. And so this becomes 2 to the n plus 1 over 3 to the n divided by 2 to the n, 3 to the n. And then multiplying the numerator by the reciprocal of the denominator, the limit as n approaches infinity of 2 to the n plus 1 over 3 to the n times 3 to the n over 2 to the n. 3 to the n's cross out. And we have 2 to the n plus 1 over 2 to the n. Now what's going to be helpful is to do a little bit more algebra. Divide the 2 to the n into both terms in the numerator. And so we get 1 plus 1 over 2 to the n. So we are looking now for the limit as n approaches infinity of 1 plus 1 over 2 to the n. And now as n is getting infinitely large, this denominator is getting infinitely large, as we've seen many times before. So this whole fraction is approaching 0, which means the limit is 1. So the limit is a number. L is 1. L is 1 here. So that means either both series converge or both series diverge. So what is it? Well, my geometric series up here, because the ratio is less than 1, it means this converges. So my comparison series converges, which means my given series also converges. All right, so I hope you found this helpful. These two examples are also in my notes, and I did the video of my doing them in my notes. Sometimes it might be helpful to see a person doing it, maybe not. And I'll see you in class.